Hello everybody. In this video we're going to learn about titration. We'll start off by covering some of the vocabulary used in titration. We'll discuss the goals of titration. We'll talk about possible reaction types that would be appropriate for titration. We will talk about the difference between equivalence point and the end point. We'll go over the titration equations and stoichiometric ratios, and then finally we'll do some example titration experiments. First, the vocabulary. The titrant is the solution of known concentration in a titration. The titrand is the solution of unknown concentration. More often these days, you're going to hear the titrand referred to as an analyte. This is the thing that we're going to analyze pretty much in any sort of experiment. The solute is a compound dissolved in a solution, and the solvent in this context is the liquid that the solute is dissolved in, and together the solute and solvent make up a solution. The equilibrium point is the point at which the moles of titrant present is equal to the moles of titrant. And so more often this is actually referred to as the stoichiometric point, because we do have to take in the account of the stoichiometric ratio between these two moles. So it's not always true that you're going to have equal number of moles of titrant and titrand, but we have whatever stoichiometric ratio is going to get us to a completed reaction. The end point is the point at which a chemical indicator changes color. A monoprotic acid is an acid with one acidic proton per molecule. A diprotic acid is an acid with two acidic protons per molecule. And a triprotic acid is an acid with three acidic protons. The goals of titration. In a titration, a known volume, because this is a volumetric technique, of titrant is added to a known volume of titrant. A reaction takes place between the solutes in the two solutions. The equivalence point of the titration is determined. The numbers of moles of titrant required to reach this point is calculated because we know the concentration of the titrant. And the number of moles of titrant is then calculated from the amount that was required to neutralize it from the titrant. When we're calculating titration results, we're going to first determine the number of moles of titrant. We'll then multiply by the stoichiometric ratio of the reaction to determine the number of moles of titrant. And then finally, we'll calculate any additional desired quantities that we want to know. This could be the concentration of the titrand. This could be the purity of an unknown solid. This could be the molecular weight of an unknown. And there's other things that we can calculate as well. Let's talk about possible titration reactions. There are titrations that are based on multiple different kinds of reactions. A couple of examples are acid-base reactions, redox reactions, precipitation reactions, or chelation reactions. This week we're going to focus on acid-base titration. Equivalence point versus end point. So to determine the equivalence point, titrations are only possible when the equivalence points can be determined. The equivalence point is determined by measuring the concentration of solution formed as the titrant and titrand is mixed. Concentration can be measured using a variety of techniques that we've seen. These could be electrochemical techniques, spectroscopy, gravimetric analysis. There are many other ways that we could do this as well. Often, however, it is not necessary to calculate the true equivalence point, but instead estimate it by finding the endpoint. The endpoint is determined by adding a chemical indicator that changes color when either the titrant or titrant is present in excess. There will always be more error when the endpoint is used instead of the equivalence point, and this is because an indicator cannot be chosen that changes color exactly at the equivalence point. But we can be careful when choosing our indicator to minimize this error as much as possible. And often a chemical indicator can be chosen that will give you really good results. Now let's talk about the titration equations. When we're given the concentration of the titrant, so we know the concentration of the titrant, we calculate the moles by multiplying the concentration by the volume required to complete the reaction with the titrant completely. So our number of moles is going to be the concentration times the volume. This assumes that we have a concentration unit that is based on moles, like molality or most often molarity. We can calculate the concentration of the titrant by dividing the moles of titrant by the volume of the titrant. So once we know the number of moles, we can divide by the volume and we will know its concentration. If instead we're given mass, the moles of titrant can be determined by dividing by the molar mass. So we can calculate the number of moles by taking the mass of something and dividing it by its molecular weight. A solution is then prepared by adding solvent until the solid is completely dissolved. And since we already know the number of moles, it doesn't really matter how much solvent we wind up using, so long as we don't get too excessive with it. Why would we use mass? This method has advantages of allowing us to determine the exact moles of titrant more exactly. This is because mass is a conservative property independent of temperature or pressure, and laboratory balances tend to be very accurate. It's one of our more accurate measuring tools that we have. Therefore, the number of moles can be determined very accurately. This method can also be used to determine the purity of a solid sample of titrant. Calculating the purity of a solid sample. So once the number of moles of titrant is determined, the mass of titrant can be determined by multiplying by the molar mass of the unknown. So once we figure out how many moles of the unknown we have, we can multiply by its molecular weight to get its mass. Dividing the mass of this titrant by the original mass of the sample, we can determine the percent mass of titrant in the sample. So we can take the mass of the titrant divided by the mass of the sample, multiplied by 100%, and we'll get our percent mass. Stoichiometric ratios. So the first thing we need to do is we need to know our reaction. In order to calculate the moles of titrant, we must know the stoichiometric ratio between the titrant and titrant species. This information can be determined from a balanced chemical equation describing the reaction. The stoichiometric ratio is essentially a conversion factor between the titrant and titrant molecules. So let's consider a few examples here with a generic monoprotic acid, that's our HA, and various generic bases. So we can have BOH, where we're going to have one hydroxide, BOH, B with two hydroxides, and B with 3 hydroxides. These would be called monohydroxyl, dihydroxyl, and trihydroxyl titrants. In these examples, these are going to be our equations for it, and you see that we increasingly need more moles of the acid to reach the same equivalence when we have this neutralization reaction. And we can write stoichiometric ratios for all of them. We can have a 1-to-1 relationship, like in this case. We can have a 2-to-1 relationship, where we're just taking the stoichiometric ratio coefficient here, putting that with the acid on top. or we could have a 3-to-1 relationship. Let's take a look at an example titration experiment. In our example experiment, we're going to start by adding an unknown acid solution, our titrant, into a flask. We'll use a pipette, so we're going to be able to accurately measure how much volume we added. We'll then add a few drops of our indicator solution. We'll then have our burette that we add our titrant to, our solution where we know the concentration, and we'll take an initial reading. We then drip in our titrant into the flask very carefully and slowly until we know a color change. Typically, you're also going to want to stir this solution as you're adding it, and then we're going to take a final reading off of our burette. The total volume of titrant added is calculated by finding the difference between the final and initial volumes. So we take our final reading that we got from our burette and we'll subtract out our initial volume, and that'll be the total volume that we added. The moles of titrant added is determined by multiplying the concentration of the titrant, which we know already, by the volume that we added. So the moles of titrant is going to equal the concentration of titrant times the volume. Next, we need to multiply by a stoichiometric ratio to determine the moles of titrant are unknown. In this case, we'll consider the case with a triprotic acid titrant and a monohydroxyl base titrant. So here we have our triprotic unknown. We're going to need 3 equivalences of base for every one of these guys here to form our salt and our 3 water molecules. So the number of moles of titrant, we're going to multiply by our stoichiometric ratio. We need 3 moles of titrant for every 1 mole of titrant, and that will give us our number of moles of titrant. The concentration of the titrant can be determined by dividing by the moles of titrant by the volume that we initially added to the flask. Now let's consider a real-world example. Consider this real-world example. A 20 milliliter sample of phosphoric acid is titrated to a phenolphthalein endpoint by the addition of 37.5 milliliters of 0.1002 molar sodium hydroxide. What is the concentration of the phosphoric acid? First, we'll write a balanced equation for the reaction. So we're going to have our phosphoric acid. We're going to require 3 equivalences of sodium hydroxide for every one of those because we've got a triprotic acid here, and we're going to form sodium phosphate in 3 water molecules. Then we'll determine the moles of sodium hydroxide. So we were given our concentration of sodium hydroxide, our titrant here. We'll multiply that by the volume that we added of it. We'll include our conversion factors because this has to be in liters because this is moles per liter, and we'll get 0.00376 moles of sodium hydroxide. Now we can multiply by the stoichiometric ratio to determine the moles of phosphoric acid. So we know that we added this many moles of sodium hydroxide. We know that we have 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. And we're going to see that it comes out to 0.00125 mole of phosphoric acid. Finally, we'll calculate the concentration of the phosphoric acid sample. So we had that many moles of phosphoric acid in our sample. The sample was 20 milliliters. Again, we'll do our conversion factor, and we can see that sample was 0.0625 molar.